Is it recording?
Yeah. So this is the week 2, part 3, and we're talking about AST 204. We're talking about the second law of thermodynamics. The first law states that there's conservation of energy. We said if you buy some oil and put it in your tank to heat the house, you should know where this energy go. How does it transfer into heat, and how does it go into your house? If you driving a car and you put a gallon of gas in there, you expect to go at least 10 miles. If you go 5 miles and you run out of gas, something is wrong. Either you're leaking gas or the engine is completely inefficient. So you should know, we should always account for energy. Where does it go from one form to another? If you're eating 3,000 calories a day and you gain a pound a week, you know why? Because there's extra 1,000 pounds energy. Energy has got to go from one, it's got to go somewhere, you know? It's not going to go be destroyed. So we talk about this concept a little bit. The second law is going to be very important to us as HVAC technician because this is the basis of refrigeration cycle. Bill is going to talk about that a lot. So since we said that energy does not get destroyed, and we know by the law of nature that heat moves from hot to cold. You agree? Pressure moves from high to low. Water moves from high elevation to low elevation. So hot to cold. So that's the law of nature. This is how things go to achieve balance. And if we want to do other way, if you want to move the water from the lake to the mountain, what are we going to do? Water pump. You're going to pump it, which means what? You're going to put energy. Yeah. You're going to put it in buckets and go up the mountain. It's going to cost you a lot of energy. Or you're going to pump it with an electrical pump. You're going to have to pump it upstairs and you have to put energy. So the same thing with an AC. Heat moves from hot to cold. If it's hot summer day, heat is going to go from the outside to the inside naturally. Do you agree? If we want to do the opposite, which actually we're doing, we're pumping heat from the inside to the outside, from the lake to the mountain, what are we going to do? We're going to pump it. We're going to put some energy. So you have to put equal or greater amount of energy to go and pump this amount of heat from inside to the outside. So this is the second law of thermodynamics. I know it sounds fancy, but it's basically how you describe AC. So it states heat moves from hot to cold, and if you want to do the opposite, you have to put in equal amount of energy. It's a fair deal. It's also intuitive, right? Think about the river, the lake and the mountains, pumping water, I'm pumping heat. That's why they call these what? Sometimes they don't call it ACs. If it does heating and cooling, what do they call it? Heat pumps. They call it heat pumps because it's pumping heat. Sometimes from the inside outside, sometimes from the outside inside. So it's a heat pump. So, to repeat, second law of thermodynamics is heat moves from hot to cold. And if you want to do the opposite, you have to pump. You have to put some energy. Simple. Is it? Think you can remember that? Things go from high to low. If you want to do the opposite, you have to put some energy.
Which is a pump.
A pump? Yeah. Either a pump and a compressor, a pump, whatever it is. You have to put some energy. And those run with energy. Is it going to be the same amount of energy? It's going to be a little bit more because there are some losses. So, and this is what constitutes efficiency. We'll talk about that. To make heat move from cold to hot, we have to put equal amount of energy. Fair? If we want to move 1,000 BTU from a room, we have to put an equal amount of energy, either 1,000 BTU or its conversion, which is 0.3 kilowatt. We said energy is the same thing, it's just different units, right? It's all energy. We're going to put in 1,000 BTU or its conversion, which is 0.3 kilowatts. Your AC is not taking BTUs, it's taking kilowatts. So kilowatts. So if we want to heat a room by 1,000 BTU, either we use 0.3 kilowatt or 0.2 gallons of fuel oil. We said it's also a measure of energy, right? How did I come up with this number? So we know that 1 1000 BTU is 0.3 kilowatt. That's a conversion rate. What about this gallon of oil thing? So 1000 BTU. How many BTUs are in 1 gallon of oil?
138,000.
Excellent. If I want to heat for only 1000, and that's 1 gallon, the fraction of that gallon is going to be 138. It's going to be a fraction of that gallon that's equal around 0.2 gallons of oil for 1000 BTU, which is going to be a small ounce. So if I burn this amount of oil, I'm going to get 1000 BTU. Make sense?
That's
Okay.
BTU then, 138,000.
Yeah, BTU. And there are always some losses. It's not going to be perfect. Life is not perfect. Some we can account for, some we cannot. Any question about that? Energy, BTU, gallons, they're all energy. They have different names, different labels, but they are the same thing. Okay. Temperature and heat. What is temperature? Measurement of heat. What is sensible heat? Heat we can measure. Latent heat, hidden heat that we cannot measure. But what is heat? Heat is a form of energy. It's a form of energy, quantity of energy. And what is enthalpy? That's little thing that we see in the psychometric chart. And it's an energy given by temperature and a given material with weight. So to make things easy to understand what is enthalpy, it's energy that is useful to us. Let's put that. Energy we can use. What kind of energy we can use? Heat, power. Steam has power, you agree?
Yes.
Steam has power. So it's power, it's energy, it's pressure, it's volume. So enthalpy, the symbol is H, M is the mass, P is the pressure, V is the density, and U is the internal energy. You do not have to remember that or even look at it. It's just to explain to you where does this came from. So somebody measured the amount of energy in that substance and told you this is enthalpy. So what I need to understand, what is enthalpy? This fancy word is, it's Greek. Forgot what it means, but anyways. Enthalpy is the useful energy to us. We can use pressure, we can use heat, internal energy, whatever energy is acquired in that material. And so you agree when you have steam, if you heat steam, does steam have energy? Yeah, you transform the heat into mechanical energy. Steam is powerful. Steam moves trains, right?
What is that equation for that?
Don't worry about it. It just tells you where does it come from. What is the component of that enthalpy? So this equation basically is this number for enthalpy that you see in the psychometric chart over there. It's a product of the mass, pressure, specific volume, which is density, and the internal energy of that matter. So this is just the dissection of what is enthalpy came from. It's not just an abrupt number that somebody put in. They can't measure it. Do we have to know that? No. Well, all we have to do is look up the number at the psychometric chart. You probably don't even have to do that. They have a calculator for that now. But just so you know, where did it come from? What is this about? What is this enthalpy nonsense here? So you know what does it mean. So you're gonna measure, if you look here, we're measuring temperature, we're measuring volume. I'm gonna pass this around. Probably it's in your refrigeration book. And based on enthalpy, you can know what is the energy inside for 1 pound of refrigerant. So if you do refrigeration, you're gonna need enthalpy as a number. You don't need to know what is the science behind it. It's just me trying to explain to you where did it come from. These things have roots. This is defined as the thermodynamic potential, designated by the letter H, that consists of the internal energy, that's U, the system, plus the product of pressure and density. Okay, too much headache. So at least you know enthalpy is what?
Energy that's useful.
To us, okay. Thanks, that's enough. Sensible heat and latent heat, we talked about that before. Sensible heat we can measure. energy put into the substance to change its temperature. We can measure it. We can see it in action. It's measuring temperature. Example, adding heat to liquid water to raise the temperature from 50 to 120. That's sensible. Heating a rock or a plate, that's sensible. You can see it getting hot. Latent heat, energy you put into the substance that does not increase its temperature. What is the example of that? Heating a bucket of crushed ice.
Yeah, you're not gonna see that.
No. Until it completely melt, if you keep stirring it, until it completely melt, then we see the increase from 32 to all the way to 212. Also for solid and liquid and gas. So they call it if you take physics, they call it the phase change temperature. Phase change meaning from solid to liquid to gas. What are the phases of material that exist for solid, liquid, gas, and they added a fourth one since I was in high school. Huh?
Plasma.
Yeah, they added plasma now. What is plasma? It's ionized gas. So after you make the material to gas, you add more energy into it, it's gonna be ionized. It's beyond me, but good for them. Let's move. Question about sensible latent heat. Make sense? Why is this important? This is good for us to understand how can we store heat. In California now they inject walls full of wax. Why? What happened? Why do we do that? When the sun hits the house in the day, it melts all the wax. It's in pockets, of course, not going to be running. During the night, this wax to cool off is going to absorb some heat to cool off the. As it's solidified, it's going to absorb some heat. It's going to cool off the house. So you can use this kind of technologies to do some modification. They do the whole energy storage is based also on melting and releasing. There is a whole science of that. But again, heat does the same thing. For an air conditioner, we're doing the same thing. For boiling water, we're evaporating water. Behind you is a complete AC dissected into a board. And we can turn it on and see how it works and how it pumps heat back and forth. Circulates. Standards for calibration. So since the beginning of physics, people always work with water. So it's always going to be the melting temperature and the freezing point. And Celsius and Fahrenheit measure different things. Fahrenheit measured salt water, while Celsius measured regular water. So we're going to say, okay, this is 0 and this is freezing. You're going to say, this is 0, this is 100. So the freezing point in Celsius is 0. This is what we get. Boiling is 100. That's Celsius. Fahrenheit, use 32 as freezing, 212 as boiling. This is how we always used to, what we used to calibrate, is tell the standards. If I want to calibrate thermocouples, if I want to calibrate any thermometer, I'll put in ice water, and that's going to be my 0. That is going to be my 0, and I will start from there. Question. We will be using mostly Fahrenheit, not Celsius. Okay, states of material. So now we're talking about water or any kind of refrigerant, latent heat and standard heat. So we have something called subcooled ice. So once you're frozen, you're frozen. If the ice is at 32, it's frozen. So what if you go below? It's just subcooled. It's cooler, but it's frozen. Temperature is not going to change, but it is subcooled ice. Then, if we add more heat, we're going to have heat diffusion that will transform ice into water. 144 BTU per pound, that's required to start melting ice. If we add more heat, the ice is going to have sensible heat, and it's going to start increasing temperature from 32 all the way to 212. We keep adding more heat, it's going to be vapor. It's going to be steam. If we add more heat, what will happen? Superheated steam. We can add more and more and more heat, and this is how we can move a huge turbine blade with steam power. Steam is very powerful. We can have steam at 5 1000 psi and almost at 600 degrees Fahrenheit. That's a lot of heat, a lot of steam. And steam is so powerful, it can cut, it can break, it can do a lot of things. A water heater in a house that's clogged, building steam, can explode and go through the roof. So steam has a lot of power. Does air have the same power? No. Steam has more power because it has water molecules in it. Very impressive. And if you look here, they give you a temperature and they give you enthalpy in BTUs per pound, which is a measure of energy per mass, which is the pounds. That's enthalpy. The energy we can use in that steam. How do we use this energy? We can use it mechanically, or we can use the heat. We can use it somehow. Do we need to know all the science? No. Just for information so you know where it comes from. It's not really practical for us now, but at least you know where it does stem from. So we talked about energy, thermodynamics, first law, second law, latent and sensible heat, and enthalpy. So if I wanna recap. So Matthew, what is the first law of thermodynamics? Fair. That's good. Energy does not vanish, does not come from nothing. Lambert, how would you say, what is the second law of thermodynamics? Yeah? And if you wanted to do the opposite? If you want to go from cold to hot? Yes? If you want to move energy from cold to hot, you have to put the same amount of work. Okay? Fair? Work.
Same amount of energy.
Yeah. Same amount of energy or work, you have to pump something into it. Think of the water going from the lake to the mountain. You have to pump it, and you have to put some kilowatts in it. The pump is around with power. Okay. Brody, what is latent heat?
It's like ice, heating of ice.
Heating of ice. Heat you cannot measure. What another way to say it too? That's correct, by the way. Hidden. What else? Phase change heat. Fancy word. How to change things. It's the heat used to change the phase from solid to liquid, liquid to gas. Lance, what would you, if somebody asked you what is enthalpy in the psychometric chapter, what are you going to say? Layman terms, from what you understand from what I was babbling about for the last half hour. Just give me something.
All right. Energy given by the temperature of the given weight of the material.
That's excellent. And Marcus, what would you also say? What is enthalpy?
Energy that we can use useful to us.
Yeah, useful to us, which is actually what you said. Useful to us, we can use the pressure to move stuff. We can use the power in the steam to move stuff, or we can use the heat.
And that's all enthalpy.
That's what
Energy
Yeah.
being used.
Useful for us.
That's all.
That's a good way to say it. Okay, I will stop here and continue the lecture on Monday. Next week is a quiz. So, you ready?
On the
Thank you.
first day.